There's something magical about looking up at the night sky, the way those countless stars seem to whisper secrets just beyond our grasp. But what if I told you those whispers aren't random? What if the universe isn't just speaking to us, but speaking in a language we can actually understand? A language woven from numbers, patterns, and stories so ancient they've shaped civilizations. This is the hidden dialogue of the cosmos, a conversation between mathematics and myth that's been unfolding since the dawn of time. And today, we're going to learn how to listen. Think about the last time you felt small under that vast expanse of stars. That feeling isn't just awe, it's recognition. Deep down, we sense there's an order to the chaos, a rhythm to the randomness. From the precise spirals of galaxies to the recurring numbers that appear in nature, the universe repeats itself like a favorite melody. The golden ratio hides in seashells and hurricanes. The Fibonacci sequence dances through flower petals and distant nebulae. These aren't coincidences, they're clues, and for thousands of years, humans have been piecing them together, using both the cold logic of equations and the warm embrace of storytelling to make sense of it all. Because here's the beautiful truth, numbers alone can't capture the full story. The cosmos doesn't just calculate, it inspires. Ancient cultures looked at the same stars we do today and saw gods, heroes, and epic tales written in the constellations. They didn't have telescopes, but they had imagination, and that imagination became the first interpreter of the universe's language. So why does this matter now? Because in a world that often pits science against art, logic against legend, we're rediscovering that both are essential to understanding the grand tapestry of existence. By the end of this journey, you won't just see the night sky differently, you'll hear it. And trust me, what it has to say will leave you breathless. So how exactly does mathematics reveal the universe's hidden blueprint? Picture this: every time a sunflower grows, its seeds spiral outward in perfect Fibonacci patterns, the same sequence that appears in swirling galaxies millions of light years away. These repeating rhythms aren't just poetic. They're proof that the cosmos runs on a mathematical operating system. Ancient astronomers knew this instinctively. The Babylonians tracked Venus's dance across the sky with clay tablets full of calculations, while the Mayans built pyramids aligned to eclipses down to the minute. They weren't just stargazers, they were decoding the universe's source code long before telescopes existed. But here's where it gets even more fascinating. Math doesn't just describe the cosmos, it predicts it. Take Einstein's equation E equals mc squared. A handful of symbols unlocked the secrets of energy, mass, and the very fabric of space-time. Or consider pi, that endless string of digits that somehow governs the curve of every planet, every star, every black hole's event horizon. Even quantum particles, those elusive specks of reality that defy logic, bow to probability equations we can write on a napkin. It's as if the universe left a trail of numerical breadcrumbs for us to follow. And the wildest part, the deeper we dig, the more universal the rules become. The same math that calculates the orbit of Mars also explains how hummingbirds hover or how stock markets fluctuate. From the tiniest quark to the largest supercluster, everything hums to the same geometric tune. That's why physicists like Max Tegmark argue math isn't just a tool, it's the underlying reality. The cosmos isn't just described by numbers, it is numbers. Which makes you wonder, if we ever crack the final equation, will it read like a theorem or a poem? Pi is more than just a number we memorized in school, it's a cosmic signature, etched into the very architecture of reality. Think about the curve of a river bending through a valley, the arc of a planet's orbit, or even the way light ripples across a pond. All of them whisper the same truth: pi is there, hidden in the geometry of existence. But here's what's truly mind-blowing: this unassuming ratio, roughly 3.14, doesn't just describe circles. It shows up in places so unexpected. It's as if the universe can't help but repeat itself. Take the spiraling arms of a galaxy, for instance. The same pi that calculates the circumference of your coffee cup also governs the vast, swirling dance of stars millions of light years wide. Or consider the way sound waves travel, the harmonics of a violin string, the resonance of a black hole's ring-down after colliding with another, all of them tied to pi's infinite, non-repeating sequence. Even in the quantum realm, where particles flicker in and out of existence, pi emerges in the equations that predict their behavior. It's almost as if the universe has a favorite number, and it's this one. Ancient civilizations sensed pi's importance long before calculators or supercomputers. The Egyptians built pyramids with proportions that hinted at its value, while Archimedes, the Greek mathematician, nearly cracked its code over 2,000 years ago using nothing but polygons and sheer ingenuity. They didn't just see pi as a tool, they treated it like a sacred key, a glimpse into the mind of creation. And in a way, they weren't wrong. Today, physicists use pi to map the curvature of space-time around black holes, to simulate the birth of the universe in supercomputers, even to search for patterns in the cosmic microwave background, the afterglow of the Big Bang itself. But here's the real mystery: why pi? Why does this specific ratio, born from something as simple as a circle's circumference divided by its diameter, echo through every layer of reality? Some scientists argue it's because the universe favors symmetry, and pi is the ultimate symmetry breaker, an irrational number that never settles, never repeats, yet underpins the most stable structures we know. Others see it as evidence of something deeper, a mathematical constant so fundamental that it transcends physics, hinting at a universe built not just on matter and energy, but on numbers themselves. And then there's the infinite. Pi's decimal places spiral on forever, never looping, never pausing. It's a number that defies completion, much like the cosmos it helps describe. Maybe that's the most profound lesson of all, that the universe, in all its complexity, isn't just defined by pi, but is in some ways a reflection of it. Endless, unpredictable, and yet somehow perfectly coherent. So the next time you look up at the night sky, remember, you're not just seeing stars, you're seeing pi in its purest form, written across the darkness in the silent language of mathematics. The golden ratio is nature's silent signature, a mathematical fingerprint pressed into everything from the curl of a fern to the spiral arms of galaxies. That number, 1.618, isn't just a quirk of geometry. It's a universal constant, a blueprint for beauty so pervasive that once you notice it, you'll see it everywhere. Take a seashell, for instance. Its growth follows an exact logarithmic spiral, each curve perfectly proportioned to the last, expanding at the precise rate of the golden ratio. It's the same pattern found in hurricanes, in the arrangement of sunflower seeds, even in the way branches split as they reach toward the sky. But here's what's truly staggering. This isn't just nature's efficiency at work. It's artistry. Centuries ago, artists like Leonardo da Vinci and architects of the Parthenon harnessed this ratio deliberately, embedding it in paintings and temples to evoke an almost subconscious sense of harmony. Da Vinci's Vitruvian Man, with its perfectly proportioned limbs, is a love letter to the golden ratio. The Parthenon's columns, spaced just so, create a rhythm that feels innately pleasing to the eye. But what if these creators weren't just inventing beauty? What if they were tapping into something far older, a code written into the fabric of reality itself? Because the golden ratio doesn't stop at human-made wonders. It's woven into the double helix of DNA, the spacing of planets in our solar system, even the way galaxies unfurl across the cosmos. Astrophysicists have found that the most massive black holes, the ones anchoring entire galaxies, spin at rates eerily close to the golden ratio. Coincidence? Or evidence of a deeper symmetry governing the universe? Some scientists argue it's the latter, that this ratio represents a kind of cosmic equilibrium, a balance between chaos and order that allows complexity to emerge. And then there's us. The human face, when measured, often aligns startlingly well with the golden ratio. The distance between eyes, the curve of a smile, even the proportions of a perfectly shaped ear, they all hint at this hidden mathematics of attraction. It's as if evolution itself has a favorite formula. But why? Maybe because harmony isn't just pleasing, it's functional. Studies show that people instinctively prefer images, sounds, even buildings that adhere to the golden ratio. Our brains seem wired to recognize and reward this pattern, as if it whispers, "This is right. This is how things should be." So is the universe an artist? Or is it something even more profound? A mathematician with an aesthetic sense, crafting reality not just with laws but with elegance. The golden ratio blurs the line between science and art, between calculation and creation. It suggests that beauty isn't an accident, it's a fundamental feature of existence, stitched into the cosmos long before the first human ever picked up a paintbrush. And that raises a tantalizing question. If the universe has a sense of beauty, what other secrets might it be keeping? What other masterpieces are waiting to be decoded in the language of numbers? Zero is the quiet rebel of mathematics, a number that doesn't just represent absence, but rewrites the rules of reality itself. Imagine a world without it, no calculus, no computers, no way to describe the moment before time began. That's the power of zero. Ancient Indian mathematicians were the first to dare give this void a symbol, a concept so radical it took centuries to spread across the world. Before zero, numbers were tethered to counting tangible things: sheep, stars, grains of sand. But zero, it was the first abstraction, a gateway to imagining nothingness as something meaningful. And that leap of thought didn't just change math, it changed the universe. Because here's the paradox: zero isn't empty, it's pregnant with possibility. Modern cosmology tells us everything, every star, every atom, every whisper of light burst forth from a state of near-perfect nothingness. The Big Bang wasn't an explosion in space, it was the eruption of space itself from a singularity, a point where all equations break down into zeros. Even now, black holes warp space-time around their cores into singularities, places where density becomes infinite and the laws of physics surrender to the void. Zero isn't the end of the story, it's the blank page on which reality writes itself. And then there's the quantum realm, where particles flicker in and out of existence like fireflies in a dark field. So-called empty space isn't empty at all, it's a seething foam of virtual particles born from quantum fluctuations. In other words, even nothingness is alive with potential. This isn't just philosophy, it's hard science. The Higgs field, which gives particles mass, permeates the universe like an invisible ocean, its average value hovering near zero, yet shaping everything from the weight of a proton to the gravity of a galaxy. Zero isn't passive, it's the silent architect of existence. But perhaps zero's greatest magic is how it bridges cultures and epochs. The Maya independently conceived of it as a placeholder in their calendars, tracking vast cycles of time. Buddhist philosophers meditated on sunyata, emptiness, as the ground of being centuries before quantum physicists described the vacuum state. Even art whispers zero's secret. The Japanese concept of ma, the purposeful emptiness between brushstrokes in ink paintings or pauses in music, reminds us that absence defines presence. Zero isn't a lack, it's the space that allows meaning to emerge. So the next time you see a zero on a page, don't just see a circle. See a cosmic cipher, a symbol that contains both the birth cry of the universe and the quiet between heartbeats. It's the reason we can calculate infinities, model black holes, and even ponder what came before time. Without zero, we'd be stuck counting stars without understanding the darkness that holds them. And that darkness, it's anything but empty. It's the canvas, the question, the beginning. Long before star charts or spectrometers, humans sat beneath the heavens and spun tales. Constellations weren't just dots of light, but epic dramas written across the night. Orion the hunter, forever chasing the Pleiades, Scorpio poised to strike, the great dragon Draco coiled around the celestial pole. These weren't random shapes. They were survival tools, maps, and moral lessons all at once. Ancient sailors navigated by these stellar stories, farmers planted by their seasonal appearances, and cultures from Babylon to the Andes wove them into creation myths. But here's what's extraordinary: those myths didn't just entertain, they became the first textbooks of astronomy. Take the Greek zodiac, for example. What began as 12 constellations tied to harvests and floods evolved into a celestial coordinate system, the very grid modern astronomers still use to locate planets and galaxies. The Babylonians, meticulous record keepers, tracked Venus's movements not just as a wandering star, but as the goddess Ishtar descending into the underworld. Their mythic metaphors hid precise planetary data, allowing later astronomers like Ptolemy to predict eclipses centuries in advance. Even today, when we say Mercury is in retrograde, we're speaking the language of myth as much as science. Across the world, the Chinese celestial menagerie azure dragons, vermilion birds, wasn't mere folklore. It was a sophisticated way to divide the sky into lunar mansions, guiding imperial astronomers to document supernovae so accurately we can still pinpoint their remnants today. The Dogon people of Mali, without telescopes, knew of Sirius B, a white dwarf invisible to the naked eye, because their oral traditions preserved astronomical observations older than Stonehenge. These stories were more than just culture, they were data storage passed down through generations like cosmic flash drives. Yet the real magic lies in how these myths refused to die. When Galileo turned his telescope to Jupiter's moons, he didn't see unnamed dots, he called them the Medicean stars, flattering his patrons just as the ancients flattered their gods. NASA Apollo missions drew names from Greek mythology, and modern telescopes like Hubble capture images of the pillars of creation in the Eagle Nebula, a name straight out of epic poetry. Science didn't erase the stories, it built upon them, proving that wonder and calculation aren't opposites but partners. So the next time you glance at Taurus or Gemini in a horoscope, remember, you're touching a thread that stretches back to the first humans who ever looked up and dared to ask, what if? Those myths were the original algorithms, pattern recognition software coded in starlight and campfire smoke. They remind us that every equation, every rocket launch, begins with something simpler and just as vital, a story waiting to be told. Pythagoras sat under the night sky and heard music not metaphorically, but as a literal symphony. To him, the planets didn't just move, they sang, each orbit ringing out a distinct note in a celestial harmony he called the music of the spheres. Centuries later, Johannes Kepler, armed with Tycho Brahe's meticulous data, took this idea and ran with it. In his Harmonices Mundi, he mapped the planets' speeds to musical intervals, convinced their movements composed a cosmic chord. Today, we know they weren't entirely wrong. the universe does hum, not with literal sound, but with vibrations so profound they shape galaxies. Take galaxy clusters, those sprawling metropolises of stars. Between them, vast clouds of superheated gas ripple with sound waves frequencies so deep they'd register as B-flat, 57 octaves below middle C, if human ears could hear them. NASA Chandra X-ray Observatory has captured these pressure waves, slow-motion tsunamis traveling through intergalactic space at hundreds of miles per second. They're echoes of ancient collisions, the aftershudders of galaxies merging like cymbals clashing in slow motion. And just like music, these waves leave patterns, ripples in the cosmic web that astronomers can read like sheet music. Then there's the cosmic microwave background, the faint glow from the infancy of the universe. Convert its temperature fluctuations into sound, and you get a haunting drone, the birth cry of reality itself. Scientists at MIT have even sonified data from black holes, turning their gravitational waves into audible chirps and rumbles. What emerges isn't noise, it's rhythm. Structure, a universe that doesn't just contain vibrations, but is built from them. This isn't just poetic coincidence. Vibrations are woven into the fabric of existence. At the quantum level, particles are tiny strings humming at specific frequencies, their notes determining whether they'll become electrons or quarks. Supernovae ring like bells when they explode, their shockwaves propagating through space-time. Even Earth's magnetic field crackles with electromagnetic whistler waves, eerie tones caused by lightning echoing through the magnetosphere. Pythagoras and Kepler glimpsed a truth modern physics confirms. The cosmos isn't silent. It's an orchestra where every atom, every star, every black hole plays its part. So why does this matter? Because it bridges the oldest myths with the newest science. The Hindu concept of Nada Brahma, the universe as sound, finds eerie resonance in string theory's vibrating filaments. Indigenous cultures from Australia to the Andes speak of songlines and creation chants that mirror the mathematical harmonies astronomers now measure. Whether through equations or allegory, humanity keeps returning to the same revelation. The universe isn't just a place, it's a performance, and we're not just audience members, we're instruments tuned to the same frequencies that strum the stars. Perhaps that's the most beautiful lesson of all. The music of the spheres was never just about sound. It was about connection, the idea that the same forces guiding planets also pulse through our blood, our breath, the firing of our neurons. When a newborn star's vibration matches the rhythm of a human heartbeat, or when the golden ratio appears in both spiral galaxies and seashells, it's not magic. It's mathematics, a reminder that we're not separate from the cosmos, we're its song, finally learning to listen. Fibonacci's sequence is more than a math puzzle, it's the universe's favorite blueprint for growth. Start counting 0, 1, 1, 2, 3, 5, 8, each number the sum of the two before it. Simple, right? Yet this humble pattern unfolds in the curve of a nautilus shell, the swirl of a pine cone, even the branching veins of a leaf. But scale up and the real magic begins. Hurricane clouds spin in Fibonacci spirals. The arms of galaxies like M74 unfurl in that same golden ratio. Even the distribution of matter in the cosmos, those vast filamentary webs connecting galaxy clusters, follows fractal patterns eerily reminiscent of this ancient sequence. So why does nature keep returning to this math, efficiency? The Fibonacci spiral packs the most growth into the least space, a cosmic cheat code for maximizing energy while minimizing waste. Picture a sunflower's seeds. Each new one sprouts at an angle precisely 137.5 degrees from the last, the golden angle derived from the sequence. This ensures every seed gets equal access to sunlight, no overlaps, no gaps. It's engineering perfected over millions of years. Now look at a spiral galaxy from above. Stars don't clump randomly. They follow that same efficient curve, gravity's version of botanical brilliance. But here's where it gets stranger. Dive into the quantum realm, and Fibonacci numbers resurface in the energy levels of electrons in magnetic fields, a phenomenon called the Hofstadter butterfly. Even the way plants grow, the timing of new branches or leaves often follows Fibonacci intervals, as if biology has an internal metronome set to this mathematical rhythm. Some scientists propose it's not just about efficiency, it's about resonance. Vibrational frequencies that stabilize structures, from DNA helices to galactic arms, might naturally lock in to Fibonacci proportions like tuning forks harmonizing. Yet the real mystery isn't where Fibonacci appears, it's why it's everywhere. Is the universe inherently mathematical, or have we simply trained ourselves to see patterns we crave? Skeptics argue it's confirmation bias, noting that not every spiral fits perfectly. But then there's the Mandelbrot set, a fractal generated by simple equations, where Fibonacci numbers emerge spontaneously in its infinite complexity. Coincidence can't explain that. Neither can it explain why black holes' spin rates cluster near Fibonacci-derived values, or why certain quantum particles arrange themselves in Fibonacci like quasi-particles. Perhaps the truth lies in the sequence's recursive nature, the way each step builds on what came before. The universe, after all, is a story of cumulative growth, stars birthing planets, cells dividing into organisms, energy condensing into matter. Fibonacci's rule, add the last two to make the next, might just be the universe's way of remembering itself. So next time you see a fern unfurling or a galaxy twirling, remember, you're not just looking at biology or astronomy. You're witnessing the cosmos doing its favorite math problem, one elegant addition at a time. Dark matter is the universe's greatest sleight of hand, an invisible force bending light like a cosmic illusionist. Picture a galaxy spinning so fast its stars should fling into the void, yet they hold together as if gripped by unseen fingers. That's dark matter's signature. It doesn't glow, absorb, or reflect light, yet its gravitational pull is so strong it warps spacetime itself, bending the path of distant starlight around galaxies like water flowing around a rock. Einstein called this effect gravitational lensing, and it's how we first glimpsed the shadowy scaffolding holding the cosmos together. But here's what defies intuition. Dark matter isn't some rare anomaly, it's the main ingredient. For every galaxy, star, or planet we see, there's 5 times more mass lurking unseen. Think of it like the wind. You can't see it, but you watch leaves dance and know it's there. Astronomers observe the same clues: galaxies rotating faster than visible matter allows, clusters colliding with their gas clouds lagging behind, as if something invisible is anchoring them. Even the cosmic microwave background, the afterglow of the Big Bang, bears fingerprints of dark matter's gravity shaping the infant universe. The hunt for dark matter reads like a detective novel. Scientists have ruled out planets, black holes, and even rogue neutrinos as candidates. Current theories suggest it could be WIMP, weakly interacting massive particles that barely interact with normal matter except through gravity. Or perhaps actions, hypothetical particles so light they behave more like waves than particles. Underground labs like Italy's Gran Sasso mine and space telescopes like Euclid are racing to catch these phantoms in action, but so far, dark matter remains just out of reach. Yet its absence tells a story. Without dark matter's gravitational glue, galaxies would never have clumped together after the Big Bang. Stars wouldn't ignite, planets wouldn't form. We owe our existence to this invisible architect, and that raises a haunting question. If dark matter dominates the cosmos, what does that mean for the laws we think we understand? Every flicker of bent light, every star orbiting too fast, is a reminder that the universe is still whispering secrets, and we've only just learned to lean in. Black holes are the universe's ultimate paradox, places where numbers bend until they snap. At their core lies a singularity, a point of infinite density where gravity becomes so strong that space-time itself tears. Picture this: if you could squeeze Earth down to the size of a marble, its gravity would crush it into a black hole. Yet what makes these cosmic monsters so fascinating isn't just their destructive power, it's how elegantly they fit into Einstein's equations. Karl Schwarzschild's solution to general relativity in 1916 predicted their existence long before we ever saw one, proving that math could outline the unimaginable. But here's where things get weird. Cross the event horizon, that invisible boundary around a black hole, and the laws of physics as we know them unravel. Time slows to a crawl, stretched like taffy by gravity's grip. Light trying to escape gets pulled backward, creating a one-way street into oblivion. Even stranger. From the outside, an object falling in would appear to freeze at the horizon, its image redshifted into nothingness, while from the object's perspective, it plunges onward, blissfully unaware of its impending doom. This isn't science fiction, it's the cold, calculated consequence of relativity. Then there's Hawking radiation, the twist that makes black holes not so black after all. Quantum mechanics says empty space isn't empty. It's a seething foam of virtual particles popping in and out of existence. At the event horizon, some of these particles get ripped apart. One falls in, the other escapes, stealing a tiny bit of the black hole's energy. Over eons, this slow leak means even the mightiest black holes evaporate, leaving behind what? A burst of radiation, a nugget of exotic matter. We don't know yet, but the math suggests black holes have a temperature, a lifespan, and perhaps even a memory encoded in their quantum waves. And what about information? Throw a book into a black hole, and according to classical physics, it's gone forever. An affront to quantum theory, which insists information can't be destroyed. This paradox led to the holographic principle, the radical idea that everything inside a black hole might be encoded on its surface, like a cosmic DVD. If true, it implies the universe itself could be a projection, with black holes as the ultimate encryption devices. Yet for all their mystery, black holes are surprisingly common. Supermassive ones lurk at the heart of nearly every galaxy, including our own Milky Way. When two collide, they send ripples through space-time gravitational waves we can now detect with instruments like LIGO. These echoes from the abyss are teaching us that black holes aren't just destroyers, they're creators too. Their mergers forge heavier elements, scatter stars, and may even seed new galaxies. So why does this matter? Because black holes are more than cosmic oddities, they're laboratories for the most extreme physics. They force us to confront the gaps between relativity and quantum mechanics, between math and reality. Every photon they swallow, every wave they emit, is a clue in the universe's grand puzzle. And as we decode their secrets, we're not just learning about black holes. We're learning the rules of existence itself, written in the language of gravity, quantum foam, and the silent scream of space-time tearing apart. Time's arrow only points one way, not because of some cosmic rulebook, but because of a simple, relentless force called entropy. Think of it as the universe's slow exhale, the inevitable drift from order to chaos. But here's the twist: without entropy, nothing would ever happen. No stars would burn, no rain would fall, no stories would unfold. The second law of thermodynamics isn't just about decay, it's the engine of change, the reason time has a direction at all. Take a melting ice cube. The molecules in that cube start in a neat, crystalline structure, but as heat flows in, they break free, scattering into the liquid. That's entropy in action, energy spreading out, possibilities multiplying. Now scale that up to a supernova. A dying star doesn't just vanish, it explodes, scattering heavier elements like iron and gold across space. Those elements become planets, oceans, even the iron in your blood. Entropy doesn't just destroy, it redistributes, weaving new narratives from the ashes of the old. But why does entropy always increase? It's a numbers game. There are far more ways for things to be disordered than ordered. Shuffle a deck of cards, and the chance of getting them back in perfect sequence is astronomically small. The universe is like that deck, constantly shuffling itself toward more probable, more chaotic states. Yet within that chaos, pockets of order emerge. Life itself is a temporary rebellion against entropy, a fleeting eddy in the cosmic current. And then there's the grand finale, heat death. Billions of years from now, when the last stars flicker out and black holes evaporate, the universe will reach maximum entropy, a state of perfect, uniform stillness. No more temperature differences, no more energy to extract, just a vast, lukewarm sea of particles drifting endlessly. It sounds bleak, but there's a strange beauty in it. Heat death isn't an accident. It's the logical conclusion of the story entropy began writing 14 billion years ago. Yet even in that stillness, mysteries linger. Quantum fluctuations might still stir the void, and some theories suggest entropy could reset in a cyclic universe. But for now, entropy is the invisible hand guiding everything from the steam in your coffee cup to the fate of galaxies. It's the reason we remember the past but not the future, why broken eggs don't reassemble themselves, and why every moment feels like a page turning in a book we can't rewind. So the next time you see leaves scatter in the wind or feel warmth fade from a cup, remember, you're not just watching chaos unfold, you're witnessing the universe telling its one irreplaceable story. What if every choice you've ever made, and every choice you didn't make, exists somewhere out there in the cosmos? The multiverse isn't just science fiction anymore. It's a mathematical possibility born from the most cutting-edge theories in physics. Take inflation theory, for instance. When our universe burst into existence, space expanded faster than light itself, stretching quantum fluctuations into cosmic structures. But here's the twist. Some physicists argue this expansion never stopped. Beyond the edge of our observable universe, new bubbles of spacetime could be constantly inflating into separate realities, each with their own unique laws of physics. Then there's string theory, which suggests our universe might be a three-dimensional brain floating in a higher dimensional space, like a sheet of paper in a vast cosmic stack. Collisions between these brains could trigger new big bangs, spawning parallel worlds with alternate histories. And quantum mechanics adds another layer. Schrödinger's famous cat, both alive and dead until observed, hints that every quantum possibility branches into its own timeline. In this many worlds interpretation, there's a universe where you took that job overseas, another where dinosaurs never went extinct, and countless more where the very constants of nature, gravity's strength, the speed of light are rearranged like dice in God's hand. But how do we test something so unfathomable? The math offers clues. Some models predict that colliding universes would leave faint imprints in the cosmic microwave background, cosmic bruises on the sky. Others suggest dark flow, the mysterious movement of galaxy clusters, could be the gravitational tug of a neighboring universe. And if string theory's extra dimensions exist, particle colliders might one day uncover their hidden geometry. The multiverse challenges our deepest assumptions. If infinity isn't just an abstraction but a physical reality, does that make our existence more meaningful or more trivial? Philosophers wrestle with this, but physicists see something else. A cosmic laboratory where every possible version of reality plays out. A place where the numbers don't stop at the edge of our universe but keep counting forever. So next time you gaze at the stars, remember, they might not just be distant suns. They could be windows into worlds where the impossible is ordinary and every story, no matter how unlikely, is being told. Numbers whisper to us across time and culture, not just as tools, but as sacred keys to the universe's hidden doorways. Take the number 108, revered in Hinduism as the sum of existence, 1 representing the divine, 0 the void, and 8 infinity. Malas used for meditation have 108 beads, mirroring the distance between Earth and Sun, measured in sun diameters 108 times. Meanwhile, the Bible's 12 apostles echo the 12 zodiac signs, 12 months of the year, even 12 notes in the chromatic scale. These aren't random digits, they're cultural fingerprints, pressed into humanity's collective consciousness as if the cosmos left breadcrumbs for us to follow. But why do these patterns recur? The ancient Babylonians divided the sky into 12 sections, laying groundwork for modern astronomy. The Maya tracked time with a 20-based numeral system, their long count calendar stretching across millennia with eerie precision. Even Pythagoras taught that numbers were divine, vibrating with the harmony of the spheres. Fast forward to today, and physicists find the same numbers lurking in nature's blueprints. 12 fundamental particles in the Standard Model, 180 degrees in a triangle's angles, the fine structure constant hovering near 137, a number so pivotal it governs how light interacts with matter. Coincidence or evidence of something deeper? The line between sacred numerology and hard science blurs when you examine cosmic constants. Planck's constant, the gravitational constant, these aren't arbitrary values. They're the universe's fixed parameters, the settings on reality's control panel. Change them even slightly, and stars wouldn't ignite, atoms wouldn't bond. Some theorists argue these constants hint at a deeper mathematical order, perhaps even a multiverse where other numbers hold sway. Others see them as proof of a cosmic code, programmed into existence like lines in a grand equation. Yet skepticism whispers back, are we projecting meaning onto randomness? The human brain excels at finding patterns, faces in clouds, shapes in stars. Cognitive science calls this apophenia, the tendency to perceive connections where none exist. But when cultures separated by oceans and millennia fixate on the same numbers, it's harder to dismiss as mere coincidence. The Tibetan Book of the Dead describes 108 earthly temptations. Ancient Vedic texts say the soul passes through 108 stages. Meanwhile, modern string theory suggests space vibrates in 10 dimensions, a number mirrored in the Sephirot of Kabbalah's Tree of Life. Perhaps the truth lies in between. Numbers might not be magic, but they are mirrors reflecting humanity's attempts to grasp the ungraspable. When a physicist calculates the odds of life emerging by chance and gets a number like 10 to the power of 40 against, it sparks the same awe as a mystic contemplating the infinite. Both are reaching for the same truth, that beneath the chaos there's rhythm, structure, a language waiting to be deciphered. So next time you glance at a clock at 12:34 or notice the Fibonacci sequence in a flower, pause. You're not just seeing digits or spirals, you're witnessing an old conversation, one where science and spirituality are just two dialects of the same cosmic tongue. And whether the universe is speaking or we're just learning to listen, the numbers remain silent and steadfast like starlight from a long dead sun. Light doesn't just travel, it defines the very fabric of reality. at 299,792 kilometers per second. It's not just a speed limit, it's the universe's way of enforcing cosmic law. Imagine throwing a ball on a moving train. To you, it might seem to fly straight, but someone outside would see it curve with the train's motion. Light refuses to play by these rules. Whether you're standing still or racing toward a star at half-light speed, a beam of light always passes you at that exact same number. This stubborn consistency, first pinned down by James Clerk Maxwell's equations in the 1860s, isn't just a quirk, it's the foundation of Einstein's relativity. Maxwell's breakthrough revealed something astonishing. Light isn't just a wave or a particle, it's an electromagnetic ripple moving at the speed the universe itself calibrates. His equations showed that this speed depends on two fundamental properties of space: how much it resists electric fields and how it reacts to magnetic ones. The kicker, those properties don't change no matter where or when you measure them. That's why light's speed is more than a number, it's a cosmic constant, woven into the laws of reality like a signature. But here's where it gets mind-bending. Because light's speed is absolute, time and space can't be. Einstein realized that if everyone measures light moving at the same speed, then time must stretch and space must warp to make the math work. This is time dilation. A clock on a speeding rocket ticks slower than one on Earth, not because of some mechanical flaw, but because the universe is adjusting its own rhythm to keep light's speed constant. GPS satellites have to account for this without relativity's corrections. Their timing would drift by kilometers every day. And then there's the cosmic horizon. Light's finite speed means we can only see so far, about 13.8 billion light-years, the distance light's traveled since the Big Bang. Beyond that, the universe might stretch on forever, but we'll never know because those photons haven't had time to reach us. It's like being in a foggy meadow where the mist hides everything beyond a certain distance. This horizon isn't just a limit, it's a time capsule. When we look at distant galaxies, we're seeing them as they were billions of years ago, their light finally arriving to tell stories from the universe's youth. Yet light's most profound role might be as the universe's storyteller. Because it travels at this fixed speed, causality holds firm. A cause must always come before its effect, no matter where you're standing. Without this rule, the universe would descend into chaos. Events could happen in any order, with no way to agree on what's past, present, or future. Light speed isn't just a number, it's the thread that stitches the cosmos into a coherent narrative. So why 299,792 kilometers per second? Maybe the better question is, what kind of universe would we have if it were any different? Faster light might erase time's arrow, blurring cause and effect. Slower light could shrink our observable universe to a claustrophobic speck. This number isn't arbitrary, it's the golden ratio of causality, the exact value that lets stars shine, life evolve, and stories unfold across the eons. And that's the real magic. Light doesn't just illuminate the cosmos, it holds it together. Quantum entanglement is the universe's most intimate whisper, a phenomenon so strange even Einstein couldn't stomach it. Picture two particles born from the same quantum event, separated by light years, yet still dancing in perfect unison. Change the spin of one, and the other instantly responds, as if space and time don't exist between them. Einstein called it spooky action at a distance, convinced it revealed a flaw in quantum theory. But decades of experiments, from Bell tests to photon measurements, have confirmed entanglement is real. This isn't magic, it's math, and it forces us to ask, what if reality isn't just something we observe, but something we participate in? Schrödinger, the same mind behind the famous cat paradox, took this idea even further. He speculated that consciousness might play a role in collapsing quantum probabilities into definite outcomes. In other words, the act of observation of looking could be what solidifies reality from a haze of possibilities. Modern interpretations like the Copenhagen school embrace this ambiguity, suggesting particles exist in superpositions until measured, like a cosmic game of hide and seek where the seeker's gaze creates the hiding spots. The implications are staggering. If consciousness and quantum mechanics are entangled, does that mean the universe needs observers to fully exist? This isn't just philosophy. The observer effect shows up in labs every day. In the double-slit experiment, electrons behave as waves when unobserved, creating interference patterns on a screen. But the moment scientists set up detectors to see which slit each electron passes through, the particles choose to act like discrete bullets. It's as if reality recalibrates itself based on what we're looking for. Some researchers, like those exploring the von Neumann-Wigner interpretation, argue this hints at a deeper truth, that mind and matter aren't separate, but intertwined layers of the same cosmic process. Yet the line between physics and mysticism here is razor thin. Ancient traditions from Buddhism to indigenous cosmologies have long described reality as participatory, a web where observer and observed co-create each other. The Taoist concept of wu-wei, or effortless action, mirrors the quantum idea that forcing a measurement disturbs the system. Even the Hindu Upanishads speak of a universe where consciousness is foundational, not derivative. Skeptics dismiss these parallels as coincidence, but the overlap is hard to ignore. When physicists like David Bohm propose an implicate order beneath observable reality, a hidden dimension where everything is connected, it echoes mystic visions of oneness across millennia. And then there's the enigma of non-locality. Entangled particles defy our classical intuition about cause and effect, responding faster than light could travel between them. This doesn't just challenge relativity, it upends our very notion of separateness. Could space itself be an illusion, a projection of deeper relationships we don't yet understand? Theologians might call this divine unity. Physicists call it quantum field theory. Both are grappling with the same profound mystery, that the universe seems less like a collection of things and more like a conversation, a dynamic exchange where numbers and narratives fuse into something greater than their parts. So where does that leave us? Perhaps the most humbling lesson of quantum mechanics is that reality refuses to be pinned down. It's neither purely material nor purely mental, but a shimmering interplay of both. The equations work, the predictions hold, yet the deeper we probe, the more the cosmos feels like a story we're writing together. One observation, one measurement, one moment of wonder at a time. And in that uncertainty, there's a strange comfort. If the universe is this fluid, this responsive, then maybe our place in it isn't just as spectators. Maybe we're co-authors, adding our own lines to an epic still being told. The constants of the universe feel almost too perfect to be accidental gravity's pull, the strength of electromagnetism, even the precise energy levels in carbon atoms that make life possible. Tweak any of them just slightly and stars wouldn't shine, molecules wouldn't bond, and we wouldn't be here to wonder why. This eerie precision is the heart of the anthropic principle, the idea that the universe's laws appear fine-tuned because, well, we're here to observe them. But is that just a tautology, or does it hint at something deeper? Consider carbon, the backbone of life. For it to form in stars, a rare and delicate resonance must exist between helium and beryllium nuclei, a resonance that depends on the exact balance of fundamental forces. Physicist Fred Hoyle famously predicted this resonance before it was discovered, arguing that without it, life as we know it couldn't exist. Was this luck or something more? The multiverse theory offers one answer. If countless universes bubble into existence with random constants, we inevitably find ourselves in one where the numbers align just right. In this view, we're not special, just statistically inevitable. Yet others see a different story. The strong anthropic principle suggests the universe must produce conscious observers, implying a deeper law or even intentionality behind the curtain. Philosopher John Wheeler took this further with his participatory anthropic principle, proposing that observers like us are needed to bring the universe into definite existence. It's a radical twist. Instead of the universe creating us, we might play a role in creating it, collapsing quantum possibilities into reality through observation. The debate isn't just academic. It forces us to confront what fine-tuning really means. Are the constants finely tuned for life, or is life simply a byproduct of the constants we have? Think of a puddle marveling at how perfectly its hole fits its shape. The hole wasn't made for the puddle simply conforms to the hole's dimensions. But then again, if the hole were even slightly different, there'd be no puddle at all to ask the question. Religion and science have danced around this tension for centuries. The medieval concept of the great chain of being saw humanity as the universe's purposeful culmination, while modern physics offers a humbler narrative. We're the temporary result of a vast, indifferent cosmos. Yet both perspectives agree on one thing: our existence is tied to the universe's deepest rules. Whether by accident or design, the fact remains, we're here because the numbers allow it. And that, in itself, is a mystery worth pondering every time we look up at the stars. Astrobiology begins with a deceptively simple question: are we alone? The universe stretches across 93 billion light-years, sprinkled with 2 trillion galaxies, each hosting billions of stars. With numbers like these, it feels inevitable that life exists elsewhere, until you start crunching the probabilities. Enter the Drake equation, a mathematical thought experiment crafted by astronomer Frank Drake in 1961. It's not so much a formula with answers as a framework for wonder, multiplying factors like the rate of star formation, the fraction of stars with planets, and the slim chance that chemistry on any given world sparks biology. Plug in optimistic numbers and the galaxy might hum with civilizations. Pessimistic ones, and Earth could be a cosmic fluke. The equation's power isn't in solving for aliens, it's in revealing how many gaps still linger in our understanding of life's cosmic recipe. Take habitable zones, for instance. Not every planet gets the Goldilocks treatment, close enough to its star for liquid water, but not so close it boils away. Earth orbits in our sun's sweet spot, but even here the margins are razor thin. A few percent closer to the sun, and we'd fry like Venus, a tad farther and freeze like Mars. Yet Kepler telescope data shows 1 in 5 sun-like stars likely hosts an Earth-sized planet in this delicate band. That's billions of potential gardens in our galaxy alone. But orbit isn't enough. A planet needs atmosphere, magnetic fields to deflect radiation, and geological activity to recycle nutrients. Jupiter's moon Europa, hiding a salty ocean beneath its icy crust, proves liquid water can exist far outside traditional habitable zones, reshaping what life-friendly even means. Then there's the chemistry. Life as we know it relies on carbon's knack for forming complex molecules, bathed in water's universal solvent. But is carbon essential, or just one path among many? The Miller-Urey experiment in 1953 proved amino acids, life's building blocks, can arise from lightning zapping a primordial soup. Since then, we've found these organic molecules everywhere, in interstellar clouds, on comets, even in the rings of Saturn. The universe seems eager to cook the ingredients. But going from amino acids to a living cell is like scattering Scrabble tiles and hoping they form Shakespeare possible, but staggeringly improbable. Or is it extremophiles, Earth's microscopic daredevils, thrive in boiling acid, Antarctic ice, even the vacuum of space? If life can cling to hydrothermal vents or survive radiation in the Atacama Desert, maybe it's not fragile. Maybe it's inevitable wherever conditions allow, which brings us back to the numbers. SETI radio telescopes have scanned the skies for decades, hearing only silence. The Fermi paradox looms. If life is likely, where is everybody? Some argue intelligent civilizations are fleeting, snuffed out by war or climate collapse. Others suggest we're like ants in a cathedral, too primitive to recognize advanced signals. Or perhaps life is common, but intelligence rare. After all, Earth hosted microbes for 3 billion years before brains evolved. Yet the most thrilling possibility remains. We're on the verge of answers. The James Webb Space Telescope peers into exoplanet atmospheres, hunting for biosignatures like oxygen or methane. Missions to Europa and Saturn's moon, Enceladus, may drill into their hidden oceans. Every discovery tightens the Drake equation's variables, turning speculation into science. Because here's the beautiful tension at the heart of astrobiology. The math can't yet tell us if we're alone, but it's teaching us how to listen. And in that listening, whether to the chemical whispers of a distant atmosphere or the radio murmur of a civilization not so different from our own, we're not just searching for aliens. We're discovering what it means to be a tiny, thinking part of a vast, mysterious cosmos. In the early 20th century, mathematician Kurt Gödel dropped a bombshell on the world of logic, one that still echoes through physics and philosophy today. He proved that even in the most rigorous mathematical systems, there are truths that can't be proven within the system itself. Think of it like a book that's missing its own index. No matter how complete it seems, it can't contain every answer about itself. This revelation, known as Gödel's Incompleteness theorem, didn't just shake the foundations of math. It hinted at something far more profound. The universe might have built-in limits to what we can ever truly know. Consider the quest to unify physics, to find a single equation that explains everything from the spin of electrons to the expansion of galaxies. Gödel's work suggests there might be questions so deep, so fundamental, that no equation can fully capture them. Take consciousness, for example. We can describe brain chemistry with exquisite precision, but can math ever explain the experience of seeing the color blue or feeling wonder? Or ponder the origin of the universe. The Big Bang equations take us back to a singularity, a point where the math itself breaks down into gibberish. It's as if the cosmos scribbled, "Here be dragons," at the edge of its own map. This isn't failure, it's revelation. Gödel showed that uncertainty isn't a flaw in our understanding. It's woven into the fabric of knowledge itself. And that's where stories come in. Before telescopes, humans explained eclipses with myths of celestial wolves swallowing the sun. Today, we use relativity. But both are attempts to name the unnameable, to bridge the gap between what we can calculate and what we can only wonder about. The Maori story of Rangi and Papa, the sky and earth locked in embrace until their children force them apart, isn't just poetry. It's a different kind of truth, one that resonates with the Big Bang's violence in ways equations alone can't capture. Science and myth aren't opposites, they're partners in the same eternal dance. When physicists talk about multiverses or string theories, hidden dimensions, they're not so different from the Norse Yggdrasil, the world tree connecting 9 realms. Both use the tools at hand, numbers or narratives, to explore what lies beyond the visible. Maybe that's the real lesson of Gödel's theorem. The universe isn't just a puzzle to be solved, but a story to be lived. And like any great story, its deepest truths might not lie in the answers, but in the questions that keep us reaching, dreaming, and gazing at the stars. Chaos isn't just disorder, it's the universe's way of hiding its most intricate patterns behind a veil of randomness. Picture a butterfly flapping its wings in Brazil, setting off a chain of events that spirals into a hurricane halfway across the world. That's the butterfly effect in action, a tiny, imperceptible change rippling outward until it transforms the entire system. But here's the twist: this isn't a flaw in nature's design. It's a feature. The cosmos doesn't just tolerate chaos, it thrives on it, using unpredictability as a creative force. Take weather, for example. Despite satellites and supercomputers, forecasting beyond a week remains notoriously difficult. Why? Because the atmosphere is a chaotic system where microscopic variations, a shift in humidity, a gust of wind, can snowball into entirely different outcomes. Edward Lorenz discovered this in the 1960s when he ran a weather simulation with what should have been identical inputs, only to watch the results diverge wildly. The culprit, a rounding error, one so small it barely registered, yet it rewrote the entire forecast. That's the essence of chaos theory: sensitivity to initial conditions so extreme that even the tiniest hiccup can rewrite the future. Now zoom out to the cosmic scale. The solar system, often pictured as a clockwork of perfect orbits, is actually a dance on the edge of chaos. Jupiter's gravity tugs at asteroids just enough to nudge them into unstable trajectories, some veering toward Earth, others flung into interstellar space. Over millions of years, these small perturbations can scatter planets from their paths. Scientists call this orbital chaos, and it's why we can't predict Earth's exact position 10 million years from now. The math works, it's just that the universe refuses to stick to the script. Then there's the quantum realm, where chaos takes on a surreal new form. Empty space isn't empty. It's a frothing sea of virtual particles popping in and out of existence, a phenomenon called quantum foam. Here, uncertainty isn't a limitation of our tools, it's baked into reality itself. Heisenberg's uncertainty principle tells us we can't simultaneously know a particle's position and momentum with perfect accuracy. The more precisely we measure one, the more the other blurs into unpredictability. It's as if the universe insists on keeping a few cards close to its chest, no matter how hard we look. Yet within this chaos lies a strange kind of order. Fractals, those infinitely complex shapes that repeat at every scale, are born from chaotic equations. A coastline's jagged edge, the branching of lungs, even the distribution of galaxies in the cosmos all follow fractal patterns. They're proof that chaos doesn't mean randomness, it means depth, layers of complexity waiting to be unpacked. The Mandelbrot set, generated by a simple formula, contains infinite variations within its boundary, a visual echo of how the universe builds complexity from simple rules. So why does this matter? Because chaos theory shatters the illusion that the universe is either predictable or random. It's both. A supernova's explosion is governed by precise physics, yet the exact moment it ignites depends on turbulent, chaotic forces inside the dying star. Life itself may owe its existence to chaos: asteroid impacts, climate shifts, genetic mutations, all unpredictable events that somehow led to us. The cosmos isn't just telling a story, it's improvising, weaving plot twists from the tiniest fluctuations. And in that unpredictability, we find something astonishing, a universe that's not just alive but endlessly, gloriously creative. String theory whispers a radical idea, that the tiniest building blocks of reality aren't dots but loops. Imagine every particle in the universe, from the quarks in your fingernails to the photons streaking from distant stars, as microscopic strings vibrating at distinct frequencies. A string humming one note might become an electron, another a quark or a photon. It's as if the cosmos isn't just governed by mathematics but composed by it, a grand symphony where the laws of physics emerge from harmonies too small to see. The elegance of this idea is staggering. For decades, physicists have struggled to reconcile quantum mechanics, which rules the tiny world of particles, with general relativity, which describes the vast curvature of space-time. String theory offers a bridge, a framework where gravity and quantum forces unite under a single set of equations. But there's a catch. These strings don't dance in the 3 dimensions we know. They require at least 10 dimensions to vibrate properly, meaning our universe might be hiding 6 spatial dimensions curled up so tightly we've never noticed them. Think of a garden hose. From afar, it looks like a simple line, but up close, you see its circular surface. Could space-time have similar hidden folds? Then there's the music itself. Just as a violin string can produce different notes depending on how it's plucked, cosmic strings might generate different particles through their vibrations. The mass of a particle would correspond to the string's tension and frequency, like tuning a guitar to play heavier or lighter sounds. This isn't just poetic metaphor. The mathematics behind string theory suggests that the universe's fundamental forces, electromagnetism, the strong and weak nuclear forces, even gravity, are all variations on a single vibrational theme. Yet for all its beauty, string theory remains controversial. Unlike the standard model, which has been tested in countless experiments, string theory's predictions are currently beyond our technological reach. Those extra dimensions, if they exist, they're likely smaller than a trillionth of an atom's width, and the energy required to directly observe strings is a quadrillion times greater than what our largest particle colliders can produce. Some critics argue this makes string theory more philosophy than physics, a gorgeous idea untethered from proof. But the theory's defenders counter with its sheer explanatory power. String theory naturally includes gravity, the one force that stubbornly resisted quantum description. It also suggests a universe teeming with symmetries and dualities, where seemingly different phenomena, like a theory describing strong forces and one describing weak ones, are revealed as 2 sides of the same coin. Most tantalizingly, it hints at a theory of everything, a single equation that could, in principle, describe every particle, every force, every flicker of existence from the Big Bang to black holes. So where does that leave us? Perhaps string theory's greatest gift isn't answers, but imagination. It paints a universe where the rigid laws of physics dissolve into something fluid and musical, where the fabric of reality hums with hidden depth. Whether it's the final word or just a stepping stone, one thing is certain: the cosmos has never seemed so alive, so dynamic, so full of unseen song. And if we ever learn to hear those notes, we might finally understand the symphony we've been part of all along. The universe didn't just begin, it launched, exploding from a single point into an expanse trillions of times larger than our observable cosmos in less than a blink of an eye. This isn't poetic exaggeration, it's the math of cosmic inflation, the theory that rewrote our understanding of the Big Bang. Picture a balloon inflating faster than light itself, stretching quantum ripples into galaxies before the first atom even formed. The numbers behind this hyper-expansion aren't just mind-bending, they're the reason you exist. Inflation solves 2 cosmic mysteries in one elegant equation. First, the horizon problem. Why does the universe look the same in every direction, as if distant regions had time to share information when light hadn't yet connected them? Second, the flatness problem. Why is space so perfectly balanced between collapsing inward and flying apart? The answer lies in exponential expansion. For a fraction of a second, around 10 to the power of minus 36 seconds after the Big Bang, the universe doubled in size at least 60 times over, smoothing out wrinkles like a cosmic iron while locking in tiny quantum fluctuations as seeds for future galaxies. Those fluctuations weren't random noise, they followed a precise statistical pattern called a Gaussian distribution, the same bell curve that governs heights in a classroom or stock market swings. But here's the kicker, the variations were minuscule, just 1 part in 100,000, yet that faint fingerprint became the blueprint for everything. Denser regions attracted more matter through gravity, eventually growing into galaxy clusters, while lighter areas became cosmic voids. The cosmic microwave background, the afterglow of the Big Bang, still bears this imprint today, a snapshot of those first quantum whispers stretched across the sky. The numbers get wilder. Inflation's energy source was a hypothetical field called the inflaton, which temporarily behaved like anti-gravity, pushing space apart instead of pulling it together. When this field decayed, it dumped its energy into creating particles, a process called reheating, literally igniting the conventional Big Bang we think of as the beginning. The equations suggest this transition released energy equivalent to converting the entire mass of Mount Everest into pure energy every nanosecond. And yet, all this violence was orchestrated with mathematical precision, fine-tuned enough to produce a universe where stars could eventually forge carbon, oxygen, and the other elements of life. Critics ask, if inflation is untestable, is it just clever numerology? Not anymore. In 2014, the BICEP 2 telescope team thought they'd found smoking gun evidence, polarization patterns in the cosmic microwave background from primordial gravitational waves, ripples in spacetime itself from inflation's explosive birth. Though later attributed partly to dust, the hunt continues with next-generation telescopes. Meanwhile, the theory's predictions about galaxy distribution and the universe's flatness keep matching observations with uncanny accuracy. The most profound implication isn't just how the universe began, but how many might exist beyond ours. Eternal inflation suggests some regions of spacetime never stop expanding, creating infinite bubble universes with different physical constants. In this view, our finely tuned cosmos isn't a miracle, it's one outcome in a multiverse where every possible set of numbers gets its turn. Whether you find that comforting or unsettling, one thing's certain: the more we decode inflation's equations, the more the Big Bang resembles not a chaotic explosion, but the first flawless performance of a symphony we're only beginning to hear. Neutron stars are the universe's ultimate alchemists, places where ordinary matter gets crushed into something beyond imagination. Picture a star 10 times heavier than our Sun, collapsing into a sphere no wider than Manhattan. The gravity here is so fierce that a single teaspoon of neutron star material would weigh 1 billion tons on Earth. That's not just dense, it's the point where atoms surrender, their electrons squeezed into protons until everything becomes a sea of pure neutrons. This isn't sci-fi, it's the aftermath of a supernova where the laws of physics twist into surreal new shapes. Time itself warps near these cosmic diamonds. Einstein's relativity predicts that gravity slows clocks, and neutron stars take this to the extreme. Stand on the surface if you could survive the crushing pull, and your watch would tick noticeably slower than one on Earth. Over years, the difference would add up, a phenomenon astronomers actually account for when studying pulsars. The spinning neutron stars that beam radiation like lighthouse beams across the galaxy. Some of these pulsars rotate hundreds of times per second, their surfaces moving at 1/4 the speed of light. The numbers defy intuition, but the math doesn't lie. These objects are nature's most precise clocks, their rhythms so steady they rival atomic timekeeping on Earth. Then there's the magnetism. Some neutron stars, called magnetars, pack magnetic fields a quadrillion times stronger than Earth's. Get within 1,000 miles of one, and those forces would unravel the very electrons in your body. In 2004, a magnetar 50,000 light-years away unleashed a burst of energy so powerful it briefly outshone the full moon, all from a star just 12 miles wide. If a similar flare happened within 10 light-years of Earth, it could strip our ozone layer, triggering mass extinctions. These aren't just celestial curiosities. They're reminders of how delicately balanced our existence is in a universe capable of such violence. Yet neutron stars also hint at cosmic harmony. When two of them collide, the resulting kilonova explosion forges heavy elements like gold, platinum, and uranium in seconds, the very atoms that make up your jewelry or phone circuitry. These collisions send gravitational waves rippling through space-time, a phenomenon we've only recently learned to detect. It's a poetic twist. The death throes of these extreme objects literally shake the fabric of reality while seeding the cosmos with the building blocks of planets and life. So what's the takeaway? Neutron stars are more than stellar cadavers. They're laboratories for the most extreme physics, places where matter, gravity, and magnetism push the limits of what's possible. They challenge our understanding, yes, but they also illuminate it, proving that even in the universe's most unforgiving corners, there's a strange, terrifying beauty written in the language of numbers. And every time we decode another of their secrets, we're not just studying the stars, we're learning how to read the universe's most dramatic love letter to mathematics itself. Detecting an exoplanet isn't about seeing it directly, it's about catching the universe in a subtle act of cosmic sleight of hand. When a planet passes in front of its star, the star's light dims by a fraction of a percent, as if someone briefly turned down a dial. That flicker, smaller than the dip caused by a moth flying past a streetlight, is how we find worlds hundreds of light-years away. The math behind this trick transit, photometry, reads like a celestial detective story. Johannes Kepler laid the groundwork 4 centuries ago with his laws of planetary motion, proving orbits aren't random but follow precise elliptical paths. Today, we've turned those equations into a planetary census, uncovering over 5,000 alien worlds, each with its own rhythm and story. Take Kepler 186f, the first Earth-sized exoplanet discovered in its star's habitable zone. Finding it wasn't luck, it was math in motion. The Kepler Space Telescope monitored 150,000 stars for 4 years, measuring brightness dips as small as 84 parts per million. Spotting Kepler 186f's trance, it was like detecting a single grain of sand drifting across a spotlight from a mile away. But the numbers don't lie. The star dimmed every 130 Earth days, revealing a planet roughly our size orbiting a dim red sun. That rhythm, regular as a heartbeat, told us something profound. Earth isn't a cosmic accident. The universe builds planets like ours on repeat. Yet not all exoplanets play by the same rules. Hot Jupiters, gas giants orbiting closer to their stars than Mercury does to ours, defy our solar system's expectations. Their existence forced astronomers to rewrite the playbook on planet formation. Then there's TRAPPIST-1, 7 rocky worlds, packed so tightly a year there lasts between 1.5 and 19 Earth days. Standing on one, you'd see neighboring planets looming larger than our moon, their surfaces possibly visible to the naked eye. These aren't just curiosities, they're stress tests for physics. How do atmospheres behave under such extreme tidal forces? Could liquid water exist on a world tidally locked, with one side perpetually scorched and the other frozen? The answers aren't just academic, they're clues to how common or rare life might be. The real magic lies in what we can't yet see, radial velocity measurements, which detect a star's wobble from an orbiting planet's gravitational tug, reveal hidden giants. Microlensing, where a star's gravity briefly magnifies light from a more distant star, can uncover rogue planets drifting between stars. Each method is a different lens on the same question: what's out there? And with every discovery, the Drake equation's variables tighten. We now know planets outnumber stars in the Milky Way. The average, at least one per star, likely more. That's over 100 billion worlds in our galaxy alone, a staggering canvas for potential life. But the hunt isn't just about quantity, it's about fingerprints. Spectroscopy splits starlight filtering through an exoplanet's atmosphere into a barcode, revealing molecules like water vapor, methane, or even industrial pollutants. Imagine a day not far off when we spot oxygen and chlorophyll on a distant world, a chemical signature screaming life. The math that gets us there, combining transit data, wobble measurements, and spectral lines, is a symphony of equations, each note a step closer to answering humanity's oldest question: are we alone? And that's the true wonder. Every exoplanet is more than a dot on a graph. It's a challenge to our assumptions, a mirror held up to Earth's uniqueness or mundanity. From lava worlds with molten surfaces to diamond planets crystallized under crushing pressure, the cosmos keeps surprising us. The numbers guide us, but the stories they tell of formation, survival, and perhaps even alien sunrises are why we keep looking up. Because out there, in the flicker of distant stars, the universe is whispering its greatest secrets, and we're finally learning to listen. Dark energy is the universe's greatest unsolved riddle, an invisible force pushing galaxies apart faster than gravity can pull them together. Imagine blowing up a balloon with dots on its surface, only to watch those dots accelerate away from each other, as if the balloon had a mind of its own. That's the eerie reality astronomers discovered in 1998 when they measured distant supernova and found the cosmos wasn't just expanding, it was speeding up. The culprit, a mysterious repulsive force dubbed dark energy, making up 68% of the universe's total energy and rewriting our cosmic destiny. Einstein flirted with this idea a century ago. His equations for general relativity included a cosmological constant, a fudge factor to keep the universe static, as everyone then believed. When Edwin Hubble proved the universe was expanding, Einstein called it his biggest blunder. But in a twist worthy of cosmic irony, modern observations suggest he might have been right all along. That discarded constant now looks like the leading candidate for dark energy, a property of empty space itself that generates negative pressure, stretching space-time apart like an unseen hand. Yet the vacuum of space isn't truly empty. Quantum mechanics tells us it's a seething foam of virtual particles flickering in and out of existence. These fleeting fluctuations should, in theory, generate energy, and calculations suggest this vacuum energy could match dark energy's effects. But there's a problem. The numbers are off by a factor of 10 to the power of 120. That's like predicting a candle's glow and getting the brightness of a billion suns instead. This worst prediction in physics hints that we're missing something profound about how quantum fields interact with gravity. Alternative theories abound. Some propose dark energy isn't constant but evolves over time, a dynamic field called quintessence, echoing ancient Greek ideas of a fifth element. Others suggest our equations for gravity break down on cosmic scales, requiring radical revisions to relativity itself. Then there's the holographic principle, the mind-bending notion that our three-dimensional universe might be a projection of information encoded on a distant two-dimensional surface, with dark energy emerging from its pixelated edges. The stakes couldn't be higher. If dark energy keeps accelerating expansion, distant galaxies will eventually vanish beyond an invisible horizon, their light unable to outpace the stretching of space. Billions of years from now, civilizations might gaze at a sky nearly empty of stars, with no clues that a vast cosmos once existed beyond their local cluster. Alternatively, if dark energy's strength changes, the universe could face a big rip, space-time tearing itself apart atom by atom, or a big crunch, collapsing back into a singularity. What makes dark energy so humbling is its refusal to fit neatly into our frameworks. It's not matter, it's not radiation. It's a cosmic wild card, reminding us that for all our telescopes and equations, the universe still holds mysteries that defy intuition. Every measurement, from galaxy surveys to the cosmic microwave background, tightens the puzzle without solving it. Yet in that uncertainty lies a thrilling truth. We're living through a golden age of cosmology, where the next observation, the next decimal point in a dataset, could crack open reality's deepest secrets. Dark energy isn't just a plot twist. It's an invitation to rethink everything we know about space, time, and the very fabric of existence. There's a provocative idea gaining traction among physicists and philosophers alike. What if the universe isn't just described by mathematics, but actually runs on it? Like lines of code in an unfathomably advanced simulation, this isn't the plot of a sci-fi movie. It's the simulation hypothesis, a serious argument that our reality might be a digital construct. At its core is a simple but startling premise. If a civilization could one day create simulations indistinguishable from reality, and if they chose to run countless iterations of them, the odds are overwhelming that we're inside one rather than the original universe. Philosopher Nick Bostrom formalized this logic in his famous trilemma. Either civilizations never reach the technological capability to simulate universes, they choose not to, or we're almost certainly living in a simulation. Given humanity's rapid progress in virtual reality and computing, the first two options feel increasingly unlikely, which leaves the third. The clues might be hiding in plain sight. Take quantum mechanics, where particles exist in blurred states of possibility until measured, as if rendering only what's observed to save processing power. Or the universe's pixelated nature at the smallest scales, Planck length, the shortest meaningful distance, could be the resolution limit of our cosmic simulation. Even mathematical constants, those perfectly tuned numbers governing physics, seem suspiciously precise, like parameters carefully set by a programmer. Astrophysicist Silas Bean and his team once speculated that if our universe is simulated, there might be detectable artifacts in high-energy cosmic rays, glitches in the matrix where the code cuts corners. But the most compelling evidence could be in the contradictions. Physicists have struggled for decades to reconcile quantum mechanics with general relativity, the tiny with the cosmic. Could this incompatibility be a sign of layered programming, like two subroutines not fully optimized to interact? Some theorists even suggest black holes might function as cosmic garbage collectors, deleting information to free up memory in the system. It's a wild thought, but not without precedent. Video games use similar tricks, lowering detail in distant objects to conserve resources. If the universe follows similar rules, it raises an eerie question: who's the player? Critics push back hard. They argue that simulating every particle in a universe would require more energy than the universe itself contains, a paradox that defies the laws we know. Others point out that the simulation hypothesis isn't falsifiable. If the simulation is perfect, there's no way to prove it's not real, but supporters counter that imperfections might exist. Just as a video game might show seams if you look closely enough, Our universe might reveal its digital scaffolding in subtle ways, like quantum entanglement's spooky action at a distance, which Einstein himself found unsettlingly unreal. Whether metaphor or reality, the simulation hypothesis changes how we see existence. If true, the cosmos isn't just speaking in numbers, it's executing them line by line. And that shifts the stakes of discovery. Every equation we uncover might not be a law of nature, but a line of source code in a grand program we're only beginning to debug. So the next time you notice the uncanny elegance of math, or the way reality seems to compute only what's necessary, ask yourself, are we the programmers or the programmed? The answer might rewrite not just science, but the very story of what it means to be. Einstein's equations don't just bend space, they twist time into knots. Hidden in the math of general relativity are solutions that permit closed time-like curves, paths where time loops back on itself like a Möbius strip. Picture a cosmic treadmill. Follow the right trajectory near a spinning black hole or through a wormhole, and you might return to your own past, stepping into a moment you've already lived. The numbers check out. The universe's blueprint, written in tensor calculus, seems to allow time travel, but here's where the story collides with itself. What happens if you go back and prevent your own birth, or hand Shakespeare a copy of his own works before he writes them? These aren't just thought experiments, they're fractures in causality, cracks in the foundation of reality as we know it. Enter the grandfather paradox, the ultimate narrative glitch. If you traveled back and erased your own ancestry, how could you exist to make the trip in the first place? Logic unravels, yet the universe abhors contradictions. Some physicists argue nature might enforce consistency through subtle corrections, like a cosmic editor tweaking events so your actions in the past always align with the future you remember. Drop a glass in 1920. Maybe it was always meant to shatter that way, your interference just another stitch in the tapestry. This self-consistent universe model turns time travel into a predetermined puzzle, where free choice becomes an illusion and every paradox is quietly resolved by the fine print of physics. But Stephen Hawking wasn't convinced. He proposed the chronology protection conjecture, a cosmic failsafe preventing time loops from forming. Think of it as the universe's antivirus software. Anytime a time machine starts to boot up, quantum effects or gravitational backlash would crash the system. Vacuum fluctuations near a wormhole might amplify into an infinite energy surge, or microscopic black holes could materialize to sever the timeline like scissors cutting a ribbon. Hawking's bet wasn't just philosophical, it was a challenge. If time travel were possible, he quipped, we'd have been overrun by tourists from the future. The silence of our history, devoid of chrononauts, might be evidence enough that the universe enforces a one-way arrow. Yet the math won't let go. Recent studies of retrocausal quantum mechanics show particles behaving as if influenced by future measurements, blurring the line between cause and effect. In labs, delayed choice experiments demonstrate that a photon's decision to act like a wave or particle can be altered after it's already been detected, as if the present is whispering to the past. These aren't time machines, but they hint that causality might be more flexible than we thought. Even cosmic strings, hypothetical defects in space-time left over from the Big Bang, could theoretically warp time into loops if they interacted just right. So who wins the equations or the paradoxes? Maybe both. Time travel might not be a free-for-all, but a tightly regulated feature of reality, accessible only in ways that preserve cosmic order. Like a river that allows eddies and whirlpools but never flows backward, time could bend without breaking. Or perhaps Hawking was right, and every attempt to revisit the past triggers a law of nature we've yet to fully grasp. Either way, the tension between numbers and narratives isn't just scientific, it's profoundly human. We're storytellers at heart, and time travel challenges us to reconcile the tales we tell with the equations we trust. The universe's answer, written in the fine print of relativity and quantum foam, is still turning the page. Cosmic inflation wasn't just expansion, it was the universe hitting the fast-forward button on creation itself. In a fraction of a second so small it defies human intuition, around 10 to the power of minus 36 seconds after the Big Bang, space itself stretched faster than light, doubling in size at least 60 times over. To put that into perspective, imagine a single atom swelling to the size of our entire observable cosmos in less time than it takes to blink. This wasn't a gentle unfurling, it was a numerical explosion. A runaway equation where gravity temporarily worked in reverse, pushing rather than pulling. And the evidence for this unimaginable growth spurt isn't locked in some theoretical vault. It's written across the sky in the faint afterglow of creation. The cosmic microwave background, or CMB, is like the universe's baby picture, a snapshot of its first light, released 380,000 years after the Big Bang. But zoom in on those microwave patterns, and you'll spot something extraordinary. Temperature fluctuations so precise they form a near-perfect Gaussian distribution, variations of just 1 part in 100,000. These aren't random wrinkles, they're quantum fluctuations from the universe's infancy, microscopic ripples in space-time that inflation stretched to cosmic proportions. Think of tossing a handful of pebbles into a pond, then watching the pond suddenly expand to ocean size. The ripples would freeze into vast, gentle waves. That's exactly what happened to those primordial quantum jitters. They became the seeds for galaxies, galaxy clusters, and the entire large-scale structure of the cosmos. Without inflation's hyper-stretching, those fluctuations would have remained too small to ever collapse into the stars and planets we see today. But how do we know inflation wasn't just a clever guess? The smoking gun lies in the CMB's polarization patterns, subtle swirls in the light's orientation called B modes. These are the fingerprints of primordial gravitational waves, ripples in spacetime itself generated during inflation's violent expansion. In 2014, the BICEP-2 team thought they'd spotted these patterns, though the signal turned out to be partly dust. The hunt continues with next-generation telescopes like the Simons Observatory, probing deeper into the CMB's whispers. Meanwhile, inflation's predictions keep lining up with observations. The universe's flat geometry, the statistical distribution of galaxies, even the absence of magnetic monopoles, hypothetical relics that should exist if the early universe had cooled slowly instead of inflating. The real magic of inflation isn't just in solving cosmic puzzles, it's in the numbers behind the curtain. The inflatoned field, a hypothetical quantum entity responsible for driving this expansion, didn't just push space apart. It fine-tuned the universe's energy density to 1 part in 10 to the power of 120. That's like balancing a pencil on its tip for billions of years. Get that number slightly wrong, and the universe either collapses back on itself or flies apart too fast for matter to clump. And then there's reheating, the moment the inflatoned field decayed, converting its energy into the hot soup of particles that fueled the traditional Big Bang. The equations suggest this process was staggeringly efficient, like a cosmic alchemist turning abstract field energy into quarks, electrons, and photons with precision that borders on artistry. Yet inflation doesn't just explain the past, it reshapes the future. Eternal inflation, a wild but plausible offshoot of the theory, suggests our universe might be one bubble in an endless froth of universes, each with different physical constants. Some might have stronger gravity, making stars burn out in millennia. Others might lack electromagnetism, leaving atoms unable to bond. In this multiverse, our finely tuned cosmos isn't a miracle, it's a statistical inevitability, one outcome in an infinite ensemble. It's a humbling thought. The equations that describe our universe's birth might also be the key to unlocking realities beyond our own. So the next time you look up at the night sky, remember, those stars, those galaxies, even the voids between them, all trace back to a moment when numbers didn't just describe reality, they built it. Inflation turned quantum whispers into cosmic shouts, and in doing so, set the stage for everything from the first hydrogen atoms to the neurons firing in your brain as you read these words. The universe didn't just grow, it performed a mathematical symphony, and we're the living proof that every note was perfect. The holographic principle flips reality inside out. What if everything we see, touch, and experience is just a shadow cast by information etched onto a distant two-dimensional surface? Imagine the universe as a cosmic movie screen, with galaxies, stars, and even your own hands playing out as projections from data encoded at the edge of existence. This isn't science fiction. It's a radical idea born from the fiery depths of black hole physics and string theory, suggesting that our three-dimensional world might be the universe's grandest illusion. It all starts with black holes, those cosmic paradoxes where gravity becomes so strong that not even light can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, its measure of disorder, isn't proportional to its volume, as you'd expect, but to the area of its event horizon. That's like saying the information content of a room depends not on how much stuff is inside it, but on the surface area of its walls. This bizarre hint led Gerard T. Hooft and Leonard Susskind to propose the holographic principle. All the information needed to describe a region of space could be encoded on its boundary, like a hologram storing a 3D image on a 2D film. String theory takes this further. In its framework, our universe could be a three-dimensional brain floating in higher dimensional space, with all physical phenomena, gravity, light, even consciousness arising from vibrations on a two-dimensional surface. Think of it like a video game. The rich, immersive world you explore is rendered in real time from lines of code stored on a flat disk. The holographic principle suggests reality works the same way. The equations governing particles in 3D space might actually be translations of simpler, flatter laws written in a language we're only beginning to decipher. But how could this possibly be true? Look no further than your everyday hologram. Shine light through a 2D piece of film encoded with interference patterns, and a fully 3D image springs to life. The holographic universe posits that space-time itself operates similarly, that the position, momentum, and properties of every particle are determined by bits of information stored on a distant surface, possibly at the edge of the observable cosmos. This would mean the universe has a maximum information density, a pixel limit akin to the resolution of a digital image. Beyond a certain point, zooming in wouldn't reveal more detail, just blurry blocks of data, a concept eerily mirrored in quantum mechanics, where measuring smaller and smaller distances requires ever more energy, as if reality hits a computational wall. The implications are staggering. If the holographic principle holds, then free will, time, even the passage of causality could emerge from how this underlying data is processed and projected. Quantum entanglement's spooky connections might just be threads in the code, linking distant points instantaneously because at the fundamental level, they're adjacent on the 2D surface. Even gravity, which resists unification with quantum mechanics, could arise as a secondary effect, a thermodynamic force like heat, rather than a fundamental one. Skeptics argue this is mathematical poetry without experimental proof. Yet recent work in quantum gravity has found startling consistencies. Calculations of black hole entropy in string theory match holographic predictions perfectly. And some versions of the AD/CFT correspondence, a theoretical bridge between gravity in higher dimensions and quantum field theories on lower dimensional boundaries, have become indispensable tools for physicists, even if the full holographic universe remains unproven. What's most beautiful about this idea isn't just its audacity, but its humility. It suggests that everything we perceive, the taste of an apple, the roar of a supernova, the curl of a galaxy, is a story being told by simpler, deeper numbers. The universe isn't just speaking in mathematics. It might be mathematics unfolding from a hidden surface where information, not matter, is the true currency of existence. And if that's the case, then reality isn't just something we observe. It's a performance, one where we're both audience and actors, decoding the script as we go. General relativity paints gravity as the elegant curvature of spacetime, a cosmic stage where planets and stars move like actors following invisible grooves. Quantum mechanics, meanwhile, reveals a subatomic circus where particles pop in and out of existence, governed by chance and uncertainty. Put them together, and the universe's two most successful theories start arguing like rival playwrights. One insists gravity is geometry, the other treats it as just another force waiting to be quantized. This isn't just academic squabbling, it's a battle for the soul of reality itself, and solving it might require rewriting physics from the ground up. Enter loop quantum gravity, a daring attempt to stitch spacetime itself from tiny, woven threads. Imagine the smooth fabric of relativity unraveled into a network of intersecting loops, a pixelated tapestry where even time comes in discrete chunks. In this framework, space isn't continuous. It's built from finite grains, each a billionth of a trillionth the size of an atom. Black holes become knots where these loops tangle tightly, and the Big Bang. Just the moment when an earlier universe's loops unraveled and rewoven themselves anew. The math here is fiendishly complex, but the promise is intoxicating. A universe where gravity finally speaks quantum fluently, without the infinities that plague other approaches. Then there's supersymmetry, the elegant hypothesis that every known particle has a hidden twin. Electrons might pair with selectrons, quarks with squarks, a cosmic symmetry so deep it could solve mysteries from dark matter's identity to the Higgs boson's puzzling mass. In this vision, gravity's quantum counterpart, the graviton, emerges naturally as part of a larger family. String theory loves this idea, weaving supersymmetry into its extra-dimensional landscapes where particles are vibrations on tiny, shimmering strings. But after decades of hunting, colliders like the LHC have yet to spot these superpartners, leaving some to wonder if nature skipped this particular symmetry. The stakes couldn't be higher. Without quantum gravity, black holes are paradoxes, objects so dense they should vanish into mathematical nonsense. Hawking radiation suggests they slowly evaporate, but what happens to the information they swallow? Quantum mechanics says it can't be destroyed. Relativity says it's crushed beyond recovery. This black hole information paradox is like a cosmic detective novel where the laws of physics contradict each other on page 1. Loop quantum gravity offers one escape route. Maybe information rebounds off the singularity, encoded in the loops like a scrambled message. String theory proposes another holograms where data is smeared across the event horizon, never truly lost. Amid these heavyweight theories, lesser-known contenders whisper alternatives. Causal dynamical triangulations treat spacetime as a mosaic of geometric shapes that glue themselves together differently at each moment. Entropic gravity suggests gravity isn't fundamental at all, but an emergent side effect of quantum information shuffling. like the way heat arises from atoms jiggling, even though no single atom is hot. Each approach dances around the same truth: the universe doesn't owe us simplicity. Its deepest layers might be stranger than any metaphor we can conjure. So where does that leave us, watching cosmic shadows, testing equations against starlight, waiting for a breakthrough? The irony is delicious. To understand the universe's grandest scales, we must first decode its smallest stitches. Whether loops, strings, or something beyond our current math, the answer won't just reconcile two theories, it'll reveal whether space-time is a stage, a symphony, or a story we've only begun to read. And when the final page turns, we might find that gravity was never the problem at all, just our limited imagination, straining to hear the universe's next line. From pi's infinite digits to the branching possibilities of the multiverse, we've traced the universe's dual dialects, the precise poetry of mathematics and the resonant whispers of myth. These aren't opposing languages but complementary verses in the same cosmic epic. Ancient stargazers saw gods in constellations. Modern telescopes decode galactic rotations with the same awe. The equations predicting a black hole's spin could fill a chalkboard, yet they echo the Hindu concept of Kali's dance, destruction and creation woven into one rhythm. Whether through Pythagoras's harmonies or Schrödinger's probabilities, humanity has always sensed a deeper pattern beneath the chaos. What's astonishing isn't just that the universe can be described with numbers, but that those numbers often feel like more than tools, they're collaborators. When the golden ratio appears in a sunflower and a spiral galaxy, or when quantum entanglement mirrors indigenous ideas of interconnectedness, it's as if reality is nudging us toward a truth neither math nor story can capture alone. Even our struggles to unify physics, gravity's curve against quantum randomness, mirror age-old myths of fractured worlds yearning for wholeness. The holographic principle's 2D shadows and the simulation hypothesis's coded cosmos aren't so different from Plato's cave or Buddhist illusions. Across millennia, we keep circling the same revelation. Reality might be stranger, richer, and more alive than any single framework can contain. So where does that leave us? Not at an ending, but a threshold. Every equation solved unveils new questions. Every myth reinterpreted sparks fresh wonder. The night sky that inspired Babylon's zodiac now fuels James Webb's infrared gaze, yet the longing behind both is identical: to know, to connect. That's the real magic. The universe isn't just a puzzle to solve or a tale to tell. It's an invitation to participate, to add our own voices to the chorus. Whether you're drawn to the crisp logic of calculus or the evocative power of legends, remember, you're not just decoding the cosmos, you're continuing a conversation that began when the first human looked up and dared to ask why. Now it's your turn. Does the Fibonacci sequence's spiral speak louder to you than the story of Orion's hunt? Or do black hole equations and creation myths feel like two sides of the same coin? Drop your thoughts below. This dialogue has spanned centuries, and your perspective is the next vital thread. If you've enjoyed this journey through numbers and narratives, hit like, subscribe, and join us as we keep exploring. Because the universe's greatest secret might just be this: its story is never finished, and neither is ours. Keep looking up, keep questioning, and above all, keep listening to the cosmos in every language it chooses to speak.